Hello everyone, I'm Charlie, and today I would like to present to you my thesis called Data-Driven Large Neighborhood Search for Combinatorial Optimization. This is the presentation I did to defend my PhD January 14, 2025. In this video, I'll go over the introduction and the background section, and then I'll have another video for each of the different articles. So let's start with the introduction. Combinatorial optimization is about discrete resource allocation. You have people that you need to assign to tasks or machines to a schedule, and these kind of problems appear in many different domains: logistics, transportation, and healthcare. The algorithms for CO are important because high quality solutions can have substantial effect on operational efficiency. If your cost structure is large, you're operating at the level of millions of dollars of revenue, you can make substantial savings by operating using an optimal solution. One of the main difficulty with these problems is that they are NP hard, which means that the difficulty scales exponentially with the number of variables. Typically, we rely on primal heuristics to find high quality solutions quickly. We've been traditionally limited by human intuitions. Heuristics development requires a deep understanding of the problem and significant research efforts. We've seen slow progress in general purpose heuristics. For example, SKIP still uses 2 decades old NNS heuristics. So we're looking at possible avenues to help us get better performance out of our solvers today. And one possible path is to exploit the machine learning opportunities. ML gives us automatic pattern detection, which means that we don't have to rely on an expert or a planner to detect those patterns and exploit them. We can generate a lot of generate a lot of data on demand via simulation. It's possible to fit very large data sets today with modern hardware. The computation effort is moved offline, and there's minor impact online. It's also a general purpose methodology, so you can apply it in various different ways. My thesis is organized as follows. We have three main articles, and each of them attack the problem in different angles. The first one is about SOS1 constraints, which model assignments in combinatorial problems. The second one is about the network design problem. And the third one is for generic MIPS. Right? I try to go as general as possible in the last paper. They all integrate in the large neighborhood search framework, which I call LNS. They leverage well-known algorithmic tools, off-the-shelf ML models, and MIP solvers. And I try to differentiate myself by having minimal training requirements and low inference costs. We discovered that there's valuable signal in the branch and boundary data. There's predictive power of sampling features, and ML integration can yield significant improvements when accuracy is high. We focus on large-scale instances rather than synthetic ones. We test on heterogeneous set of problems. We are solver agnostic. Also, we emphasis on high-quality data rather than the ML architecture. And finally, we aim to provide simple yet effective methods that can act as baselines. It's a new field, and we're still missing good basic methods to compare ourselves against. So let's go over the background section. We can organize these hybrid methods in two main broad categories. On the one hand, we have end-to-end CO learning, and on the other hand, we have ML augmented CO. These are the typical way that we organize the spectrum of algorithms according to the surveys of Bengio, Kotari, and Scavuzzo. In end-to-end learning, we start with a problem, we feed it into the ML model, and we directly generate a solution. However, we still have open research questions on how to handle this effectively. How to ensure differentiability on discrete structures with constraints, for example. Differentiability is a concern on discrete structures because the gradient is not well defined. And also constraints cannot be natively enforced in neural networks by default. That's why ML-enhanced CO is our preferred approach, because it allows us to leverage CO solver's capabilities. So instead of directly generating a solution from the ML model, we produce a prediction that then we feed into the solver to guide the search. CO solvers under the hood use branching. It's the branch and bound framework. And a lot of researchers have studied how to improve learning, have improved branching via learning to branch idea. You can try to learn which variable to select at every node or which node to explore next. From my lecture of the literature, ML-enhanced branching strategies have a marginal impact on the number of nodes in the branch and bound tree. So if you have a very large instance, doing learning to branch might not give you sufficient benefit or performance gains to justify the complexity, the additional complexity of doing learning. Also, maybe more importantly, it's impractical to implement in state-of-the-art solvers due to their black box nature. So for example, Gurobi, you cannot overwrite the branching rules directly. You have some control, but it's very limited. That's why we prefer to work with heuristics, either construction or improvement heuristics. One very popular scheme that's used is the local branching scheme, which defines a neighborhood defined by some distance parameter KLB. And this framework helps us define neighborhoods and trying to learn, for example, what could be a good initial feasible solution to build the neighborhood around, or to try to tune, to learn to tune the distance parameter. This is the general framework as we understand it, the ML-enhanced large neighborhood search framework, where you start from the left with instance features, a starting solution, you feed that into an ML model, and then the ML model gives you some indication for each variable, whether or not that variable should be used or not, or fixed or not. After that, you can reduce the size of the problem based on the ML prediction to produce a model that is smaller, will be easier to solve for the solver, and produce new solutions quickly. This is the general idea. So this was the introduction, the background section. The next video, I'll go over the few articles in my thesis. Thank you for watching. Bye-bye.